This is Donna Nelson, the University of Oklahoma, giving the second lecture, filming the second lecture for my organic chemistry class. This is chapter 2, the second lecture, and so we're going to be talking more about molecular representations, and in particular, for this second class, we're going to be discussing resonance and the curved arrows that are used in resonance, and how formal charges are used in resonance structures. So, pi bonds and formal charges can be more spread out than a bond line structure shows. Consider this cation. This is the allyl carbocation. The pi bond and the positive charge are really interacting. This positive charge is spread out over this 1, 2, 3 carbon unit. There's a p orbital on carbon 1, a p orbital on carbon 2, and a p orbital on carbon 3. So this pair of electrons in this pi bond is actually delocalized over all 3 of these carbons, and we're going to look at that in more detail. So here, this is the same molecule that you saw on the previous slide. So on the previous slide, this is the bond line notation. Here you have a carbon-carbon bond. We're interested in the pi system. We're not interested in the sigma system, just the pi system. So this pi bond is going to be formulated from a p orbital on carbon 1 and a p orbital on carbon 2. Then there's going to be an empty p orbital on carbon 3. So let's look at that. Here is the sigma system, which we are not interested in. It's just a framework to hold the pi system. So here is the pi system. These are each a p orbital. Okay, there's a p orbital here, a p orbital there, a p orbital there. Remember, the p orbital goes above and below the plane of the sigma system. And so these are parallel to each other. And so they overlap sideways. Okay, most reactions occur end-on through the interaction of end-on orbitals, but this overlap is occurring sideways, above and below the plane. And so this is bonding. This is a bonding. Now, it's very important for you to recognize that these are p orbitals. A p orbital is an atomic orbital. A p orbital resides on one atom. That's why it's called an atomic orbital. Here, these 3 orbitals, atomic orbitals, taken together will give an idea. In other words, they will approximate a molecular orbital. A molecular orbital shows the bonding among the different atoms. Here, these atomic orbitals are not really showing any bonding. Do you see the gap there? But when they're drawn like this, it helps you to envision the bonding. Okay, so it's very important to recognize the difference between atomic orbitals and molecular orbitals. Atomic orbitals, when drawn like this, are often used to give an approximation of what the molecular orbital looks like. And it's fine to use that so long as you remember it's an approximation and they are not molecular orbitals. You cannot get those confused. So when you have electron density that is shared across more than just 2 atoms, remember there are 2 atoms in a bond. When you have electron density shared across more than 2 atoms, that is said to be delocalized. So let's look next. So now look at this. So do you see this orbital, how it's drawn, you still have the red above the plane and blue below the plane. Do you see how you have the red lobes above the plane and blue below the plane? And you have nodes at each nucleus. And so now, if you can envision these to overlap and become molecular orbitals, now you see the red lobe of the molecular orbital. And here you see below the plane of the atoms, below the plane of the sigma system, you can see the other lobe of this molecular orbital. Do you see how this goes across the atoms? This orbital is not localized on individual atoms. This is a molecular orbital. So this molecular orbital is a bonding molecular orbital. Notice there are no nodes in this molecular orbital. And you have the top portion and the bottom portion. Here is another molecular orbital for this 3-carbon atom system. Okay, and then another molecular orbital. All of these are molecular orbitals. This is the bonding molecular orbital, non-bonding, anti-bonding. Notice that as one goes up in energy, the number of nodes in the molecular orbitals increases. So here there's no node except the one in the plane, which is always going to be there in pi systems. But here you have an additional node, and so there is not bonding here, but also there's no interaction between these orbitals of different signs. Okay, so this orbital, this non-bonding molecular orbital, is neither bonding nor anti-bonding because there's no interaction here. There's a node at this carbon atom, so there's no interaction across that carbon atom. Up here, when you go on up in energy, you can see the number of nodes increases the same way that the energy increases. This is the highest energy of these molecular orbitals, and you can see there's a node here between C2 and C1, and then there's a node over here between C2 and C3. So you have 2 anti-bonding orbitals in addition to the, or rather 2 nodes in addition to the node that lies in the plane of the carbon skeleton. So when 3 p orbitals are brought in to form a pi system, 3 p orbitals, that's 3 atomic orbitals. Those 3 AOs, which means atomic orbitals, will form 3 MOs, which means molecular orbitals. So that's why you have 3 molecular orbitals, because 3 p orbitals overlapped to form these 3 molecular orbitals. So however many p orbitals it is that overlaps, that's the number of molecular orbitals you will have. So you don't lose or gain orbitals as you're going along. So you can have, of course, 2 electrons occupy the bonding orbital, up to 2 electrons occupy the non-bonding, and you could have 2 electrons occupy the anti-bonding orbital. If you have electrons occupying the anti-bonding orbital, that will serve to destabilize the molecule. You'll start to break bonds. That's why it's anti-bonding. It will start to decompose. The bonds will start to break. So let's look now if the allyl carbocation has a charge of +1, remember what the allyl carbocation looks like. Let's go back and look. Here's the allyl carbocation. You have 2 electrons in the pi system. You have the third p orbital with no electrons in it. So these 2 electrons will go all the way across the pi system. And so if you look at it, these 2 electrons will go in this lowest energy bonding molecular orbital. So 2 electrons will go in here. You will have 0 in the non-bonding molecular orbital and 0 in the anti-bonding. The electrons will go into the lowest energy molecular orbital first. Now this is very symmetrical, and so those 2 electrons will be spread out over the entire atom. Now, because one of the p orbitals was unfilled, that means that you've got this 3-carbon system that has only 2 electrons in it, and it's going to be bearing a positive charge. And so that tells you this non-bonding molecular orbital, notice it's symmetrical. Okay, there's this carbon, even though they're of different sign, it is still symmetrical. And so the positive charge is going to be borne equally between these 2 terminal carbons. If an electron is put into this non-bonding molecular orbital, that electron density will be shared equally between these 2 carbons. Okay, because this molecular orbital covers those 2 carbons, and any electrons that are put in there will be shared equally between those 2 carbons, because that's what that molecular orbital does. So, but how do we depict that using bond line notation? So we can't depict it with just this structure or that structure. It takes both structures. And so we have these resonance structures. So the resonance structures are drawn using this double-headed arrow. So this arrow is special, and it is used only in drawing resonance structures. If you see that arrow, that tells you you're dealing with resonance structures. And also the resonance structures will be put in brackets to indicate that you don't have this structure and you don't have that structure. You've got sort of an average of those 2 structures. Okay? And so those 2 resonance structures are taken together in describing the one compound. You do not have a structure, a molecule, that is jumping back and forth between these 2 structures. It is only one structure that resembles both of these together simultaneously, sort of like an average of those 2 structures. You can think of it that way. So here we have it again, 2 resonance structures. Notice the brackets, notice the double-headed arrow, notice the positive charge at the 2 termini, and this is another way to draw it. You can draw it by using dashed lines to indicate that there is one carbon-carbon pi bond in here, and there's a partial positive here, a partial positive there. That is because this positive charge is sort of smeared out across the whole molecule, and so you're going to have part of it at one end and part of it at the other end. They are not jumping back and forth. This is not vibrating back and forth between 2 distinct structures, and it would not be possible to isolate one structure and then do something different and isolate the other structure. Okay, these are 2 drawings, and both of them are needed together to depict one molecule. This is an analogy that's given in your textbook. A nectarine is a hybrid formed by mixing a peach and a plum. You can't separate the peach and the plum. They are combined. It takes both parts to be a nectarine, and the nectarine isn't vibrating back and forth, being a peach part of the time and a plum part of the time. So that's a good analogy that your textbook has used. Delocalized electrons are spread out, and any time that anything is done to spread out a charge, whether it's a positive charge or a negative charge, that stabilizes the charge. Spreading out the charge density stabilizes the molecule, always, regardless of the method that is used to stabilize the charge. And there are going to be a lot of different methods, but the one thing that's in common is if the charge is spread out, the ion is stabilized. And that also includes radicals. If the unpaired electron density is spread out, say by resonance, that stabilizes the radical. And you'll see that later in our chapter on radicals. So the delocalization of charge, the charge is spread out over more than one atom. The resulting partial charges are more stable than having the positive charge localized on one atom. So the resonance stabilizes the molecule, always, every time. So how are we going to draw this? Notice that there is a tail and a head to these arrows. And the curved arrows always indicate the movement of electrons. Okay, so this arrow is showing the pi electrons in this carbon-carbon double bond. The pi electrons are moving over, and they will become pi electrons and a carbon-carbon double bond here. And when they move over, this positive charge will move over there, because as they move over here, the electron density will be moved off of this carbon, and so a positive charge will be generated on that end of the molecule. You will use these curved arrows constantly in organic chemistry, especially the farther along you go. When you, after, say, chapter 7, you will use them constantly in probably every lecture. You will draw mechanisms that in which each mechanism may have up to 20 arrows in it, showing the movement of electrons. And as you go along, mechanisms will become more and more complicated, in which more and more arrows are shown as more and more bonds and pairs of electrons are moved. So it's really important to learn all of these. It's very important to watch all of these filmed lectures. If you don't watch the filmed lectures, you won't learn anything. That's my opinion. So there's specific rules for using these curved arrows. The curved arrows are used to depict electron delocalization. Here in this case, we're discussing resonance. Later, we'll use the curved arrows to depict bonds being broken, sigma bonds being broken. But right now, we're only discussing resonance, and resonance is part of the pi system. And so here, this sigma bond is not part of the pi system. Okay? And so you would never break a sigma bond when you're discussing resonance, the delocalization of electron density through resonance. That's what resonance is the delocalization of electron density. And so you will not break a single bond. Okay, so here, this is depicting this pair of electrons moving in, forming a pi bond, and this plus is indicating that molecule plus this molecule. That won't happen. Don't do that. This is not resonance. That's inappropriate. You never exceed an octet for second row elements. Okay, you just don't do it. The valence shell of one of these atoms has only 4 orbitals. It'll hold a maximum of 8 electrons. Notice here, this pair of electrons moving in would cause a double bond to be formed here. Carbon would have 5 bonds. Here, this pair of electrons moving in would cause nitrogen to be surrounded by 10 electrons. It just doesn't happen. Just don't do it. These are all examples of things that don't happen. You can look at these other two and see why they would not happen. Either, you're going to have oxygen surrounded by 10 electrons, and here you would have carbon surrounded by 10 electrons. So it just doesn't happen. You might want to look carefully at those. Second row elements may have fewer than 8 electrons surrounding them, particularly in carbocations. Do you see how this pair of pi electrons has moved out onto oxygen? Now oxygen is bearing a negative charge. The carbon is bearing a positive charge. This carbon is surrounded by 2, 4, 6 electrons. It does not have the stability of a filled octet. Notice the brackets and the double-headed arrow. That designates resonance structures. So these are 2 valid resonance structures. And what this is depicting, it is depicting that oxygen pulls electron density onto itself and off of carbon. And that's what you would expect, because oxygen is higher in electronegativity than carbon is. You may remember that oxygen is second highest in electronegativity, second only to fluorine. So you can remember that as oxygen is attached to other atoms. Oxygen will be bearing a lot of electron density and cause the atoms next to it or bonded to it to be depleted of electron density. Now, when using curved arrows to create resonance structures, there may be 1 or more formal charges that you'll deal with. It may be needed, a formal charge or 2 may be needed for a valid structure. Look at this resonance structure. So if you pull a pair of electrons in to form a pi bond between carbon and oxygen, and this pair of electrons moves out to reside on carbon, so what will that cause? What will be the product of this? What will go over here? What's the other resonance structure? So this oxygen is going to bear a a positive charge. When it donates electron density, it will be a positively charged oxygen. And this carbon, since it's accepting a pair of electrons, it will be negatively charged. You should stop the video or pause it for a minute and try to draw this structure. And you can draw, this is what you would draw, but the formal charges are missing. So this oxygen will have a formal charge of +1. This carbon will have a formal charge of -1. So this structure is not correct. This structure is correct. A structure that is missing the formal charges is not correct. So that takes care of resonance. And now in the next lecture, we will go on with chapter 2 and finish the chapter at that time.